This is 1.7, which is redox. So 6 points here to be aware of. The first one is to be able to calculate the oxidation state for an element in a compound or ion, including peroxides and metal hydroxides. The second is to define the term redox and explain oxidation and reduction in terms of electron transfer and changes in oxidation state. Third is to demonstrate understanding that oxidizing agents gain electrons and are reduced, and reducing agents lose electrons and are oxidized. Number 4 is to define disproportionation and use oxidation numbers to classify a redox reaction as disproportionation. Number 5 is writing half equations and combining the half equations to give a balanced redox equation. And number 6 is using Roman numerals to indicate the oxidation number when an element has compounds or ions with different oxidation numbers. For example, chlorate 1 and chlorate 5. So, very importantly, oxidation is the loss of electrons and reduction is the gain of electrons. And redox is when oxidation and reduction occur in the same reaction. So we start by looking at oxidation states. So the concept of oxidation states or oxidation numbers, and it could be called either, is used to account for electrons. So the oxidation state or number of an atom shows the total number of electrons which have been removed from an element in a positive oxidation state or added to an element to give a negative oxidation state to get to its present state. It can alternatively be described as the charge on an atom would have if the bonding it was involved in was fully ionic. And oxidation states are determined using a series of rules. So we'll look at those now. So the oxidation state of an atom in its elemental state is 0. So for example, sodium would just be 0. The oxidation state of a simple ion equals its ionic charge. So for example, Mg2 plus is plus 2 and Cl minus is minus 1. So the oxidation state of fluorine in any compound is always 1. The oxidation state of oxygen in any compound is minus 2, with one exception, which is, well, two exceptions, which is in a peroxide, it's minus 1, or fluoride, it's plus 2. So the oxidation state of hydrogen in any compound is plus 1, except when in an ionic hydride when it's minus 1. So for example, if you have sodium hydride, the sodium be plus 1, the hydrogen be minus 1. And the sum of the oxidation states in any species equals the total charge on the species. And that's true for any compound or complex ion. So looking at a couple of examples here. If we take the example of SO3, it's a neutral compound. So if we imagine we want to find out the oxidation state of sulfur, if we imagine it as X, so we're saying here X plus 3 minus 2, and that's from the oxygens. So 3 oxygens at minus 2 each. That all adds up to 0. So that means that the X equals 6 in this case. So the oxidation state of sulfur is plus 6. And in this one, Cr2O72 minus, the overall charge is minus 2. And again, if we imagine the chromium is equal to X, so 2X plus 7 times minus 2. And again, that's from the oxygens, gives us a total of minus 2. So X equals 6. So the oxidation state of chromium in this case is plus 6. Sometimes we use Roman numerals because some elements can exhibit more than one oxidation state. So the Roman numerals are used to indicate the oxidation state of the element in these cases. So for example, chlorine can exhibit a number of oxidation states when bonded in a molecular ion to oxygen. So bleach contains the hypochlorite ion, which is ClO minus, and here the chlorine atom has an oxidation state of plus 1. And the ion is named as chlorate 1 with the Roman numeral 1 in brackets using IUPAC nomenclature. So chlorine can also bond with oxygen to give the chlorate ion ClO3 minus, in which the chlorine atom has an oxidation state of plus 5. So this is named as chlorate 5 using IUPAC. Now here's an example of chlorine and sodium hydroxide giving us sodium chloride, sodium chlorate and water. And in here the oxidation number of chlorine increases from 0 in Cl2 to +1 in the chlorate, so it's oxidized. So the oxidation number of chlorine also decreases from 0 to -1 in sodium chloride, so it's reduced. So what's happening here is the oxidation and reduction of chlorine is in the same reaction, and it's called disproportionation. So if it's going from one oxidation state changing to two other oxidation states, so we have the +1 in here and the -1 in here, so it's being oxidized and reduced in the same reaction, it's disproportionation. Now, half equations. So if we take the example of magnesium reacting with hydrochloric acid to form magnesium chloride and hydrogen, it's a redox reaction, and we can represent it by two half equations which illustrate the electron transfer process. So if we look at the magnesium here, it's going from Mg to Mg2 plus, and getting 2 electrons as well, so that's oxidation. And then the hydrogen, it's going from hydrogen ions to hydrogen gas, and that is reduction. And you see the electrons appear on different sides of the reaction. So in oxidation it's on the right, and in reduction it's on the left. So magnesium is oxidized as it loses electrons, and its change in oxidation state is from 0 to +2, and it acts as a reducing agent as it causes the hydrogen ions to gain electrons, and the hydrogen ions are reduced. They gain electrons and decrease in oxidation state from +1 to 0, and they act as an oxidizing agent as they cause the magnesium to lose electrons. So an oxidizing agent is an electron acceptor. Try that again. An oxidizing agent is an electron acceptor, and a reducing agent is an electron donor. So make sure you know the difference between something being oxidized and being an oxidizing agent. So when we come to do the half equations, the first thing you want to do is to write the formula of the species before and after the change, and then balance if required. Then you're going to determine the oxidation state of the atom undergoing the change before and after the change. You're going to add electrons to the side so that the oxidation states balance, and if the charges on the species on either side of the equation do not balance, then you're going to add hydrogen ions to one of the sides to balance the total charges. And then the next thing, to balance up those hydrogen ions that you've added, you're going to add water molecules to balance the equation. The easiest way to talk about that is with an example. So here we're looking at the reduction of manganate 7 to manganese 2. So we've got MnO4 minus going to Mn2 plus. The oxidation states then +7 and +2. So the difference there is +5, so we need 5 electrons. And then we look at the overall charges. So here we have 1 here and 5, so that's -6 on this side and +2 on this side. So we have to add 8 hydrogens to get us a total charge of +2 on each side. And then because we've added the 8 hydrogen ions, we have to add 4 water molecules to balance that up. And then we talked about disproportionation before, so if the same species is oxidized and reduced in the same reaction, it's disproportionation. So the example here is chlorine and aqueous sodium hydroxide, which we saw before. So the chlorine decreases in oxidation state from 0 to -1 in sodium chloride, and at the same time it increases from 0 to +1 in the sodium chlorate 1. And an overall equation can be constructed for a redox reaction by combining the two half equations. So the number of electrons transferred in each half of equation must be the same. Let's look at a little example of that. if we look at the example of the reaction between iron 2 and MnO4 minus, that's the one that we've just seen and just balanced up above. So we need to look at the iron, so Fe2 going to Fe3 plus an electron. Now because we have 5 electrons in this equation, we need to have 5 in this one. So we multiply it by 5, which gives us the second equation here, 5Fe2 plus 5Fe3 plus 5 electrons. And what we're doing is simply adding those two together and writing everything down then down below. So if we take the MnO4 minus plus 8H plus 5Fe2 plus, we don't need to worry about the electrons because they appear on both sides. And then on the right hand side, that's giving us Mn2 plus 4H2